So we're continuing our discussion here on seafloor spreading and evidence that the continents are moving and convection is happening. We already did evidence number 1, which was looking at the age of the seafloor. We looked at evidence number 2, which was sediment thickness across the seafloor. Evidence number 3 is still within the seafloor. But we're looking at a different set of data, this time magnetic reversals, which is probably something you're not familiar with. So we wanted just to give you a little background on that before we look at the actual data. So here's what we know. Earth has a magnetic field because of its special characteristic of this liquid outer core layer. So the liquid outer core being made of basically molten metal, as the Earth rotates, that liquid rotates along with it and creates this magnetic field that we of course can't see around the outside of the Earth. It has a few purposes that we know of. One is it does protect us from something called solar wind. So when the sun has those sunspots and sends off bursts of energy with extra charged particles, this magnetic field acts like a shield from those particles, which could potentially rip away our atmosphere. So super thankful that we have magnetic reversals. You also maybe know that the magnetic field is the reason why compasses work. So when we think about this characteristic, we're talking about the core and the magnetic field. What does this have to do with the ocean and plate tectonics? Well, here's what we know. The oceanic crust is made up of basalt, right? That igneous or volcanic dark colored rock. So it was formed by cooling magma or lava on the surface of the Earth. These volcanic rocks are really iron-rich materials, which are magnetic materials. Now, the rock itself can't hold a whole magnet usually, but little tiny crystals within the rock still align with our Earth's magnetic field. So let me show you what that means. These little magnetic minerals are floating around within lava when it's in its molten state, or magma in its molten state. So kind of like this, right? These little blue lines, these are just the crystals in their liquid state, moving around within the lava. Nothing really showing here. However, as that molten material begins to cool, those crystals, this is not what I wanted, those crystals begin to align themselves just like a compass. Those crystals went from having no particular pattern to being cooled in a very specific pattern, aligning themselves either north or south, depending how the magnetic field is oriented. So again, this is what a compass looks like, right? The little crystals orient themselves to the magnetic field. And they're solidified and essentially saved that way in the basalt that we can find on the ocean floor. So it's like each one of these little crystals is acting as a compass, recording what the magnetic field was like in the past. And that's important because there are two types of polarity that we see within the rocks. There's something called normal polarity, which you can go ahead and write in underneath your picture there. Normal polarity is when we see those small crystals pointing towards the north. And we call that normal polarity because this is where the Earth is now. This is our current magnetic field stage. So you can see the visual on your sheet and on the screen here. That's what the normal polarity looks like. But we also have something called reverse polarity, and you can see when you compare how those arrows look, it's simply a reverse of that typical direction. So the second blank that you have down there on the bottom should be reverse polarity. And again, same thing. Those crystals are cooling and aligning to the magnetic field at the time when they were created. So if we go back to our original data, we have the youngest ocean rock at the ridge, oldest far away. We're seeing changes in this magnetic field pattern across the ocean floor. In this particular diagram we're looking at, the dark is what we're calling normal polarity. So we see that pattern going across the ocean floor, alternating on either side of the ridge. And the reverse is doing the same thing, alternating on either side of the ridge. So hopefully this is starting to look a little bit familiar. Same as our age data, same as our sediment data. We're looking at this pattern happening symmetrically on either side of the ridge because of what's going on, as always, underneath. That molten material rises up from underneath, some oozes out, creating that force to push the plates apart, while most of the material separates underneath the crust, again, adding to that driving force of the plates and therefore the continents getting further and further apart, right? This is our South America, this is our Africa, so they're slowly separating over time. So you have a couple questions here to look at. Kind of just covered this one, right? How would we describe the pattern of reversals relative to the mid-ocean ridge? So this is, of course, the mid-ocean ridge. When we compare one side to the other, do we notice it being symmetrical or not asymmetrical? Hopefully this is ingrained enough in your mind to, even without seeing the picture, we know that's what we're going to experience at the mid-ocean ridge. And then number 4, you're looking here to see which layer would essentially be the twin to layer X. So we're observing this layer here as layer X. Where would the twin layer be to layer X? So you have a spot on your sheet there to fill in your choice of either A, B, or C. And then the following question is essentially why? Why are you choosing that particular layer as the twin? And what twin characteristics might they have, being that they are on the same side, or the opposite sides of the mid-ocean ridge, right? So what two characteristics might those layers share because they are quote-unquote twins? Last question then is just bringing it all together. How is this pattern of symmetry on either side of the mid-ocean ridge supporting this idea of seafloor spreading? So why is this symmetrical pattern explaining what's going on down here? The last thing you're looking at on your sheet is this short fill-in-the-blank summary paragraph where you're naming all 3 pieces of evidence that we discussed for seafloor spreading, not just the one in this video, but the 2 from earlier in class. You have a few spots to circle up the best answer that fits the statement, and 1 more fill in the blank. This is a really good lead in to your learning target 4, so check that out, and we'll also look at it a little bit in class as well. As always, reach out with any questions you have, and we'll talk soon.